Now, let's look at the issue in raster encoding of location uncertainty due to raster representation. To understand location uncertainty, you need to remember the difference between accuracy and precision. Precision versus accuracy, they don't have the same meaning. Precision refers to our ability to repeatedly measure something to a certain number of decimal places. So for example, how well can an instrument reproduce a measurement given the same environmental conditions, for example? If you're using a GPS, how close are subsequent GPS measurements to each other? Note that this has nothing to do with how accurate those measurements are, just how well they can be repeated. Also, precision has something to do with the number of digits used to report a measurement, in that we could be very, very precise with a measurement, far more precise usually than we can be accurate. So that means how many decimal places something would be reported to. And we're not necessarily interested in that idea here, but in the idea that precision is the ability to reproduce measurements given the same conditions. How close are those measurements to each other? So accuracy refers to how close a measurement is to its true value in the real world. For example, if you find a fire hydrant, how closely can you measure the coordinates of that fire hydrant against some model of the Earth? Measurements can be precise and not necessarily accurate. For example, we have these different conditions or cases of imprecision and accuracy. So inaccurate and imprecise is in the first case here. Here, our true location coordinate is at the crosshairs of that grid. So where the X and Y axes meet. That's the true measurement that we're trying to get. And if we have a lot of spread of measurements around there, like that, we would say we have something that's inaccurate and imprecise. Inaccurate because they're not very close to the true value right here, and imprecise because on repeated measurements, they are in fact showing very different locations. In the second case, right here, we have something that's inaccurate and precise. So inaccurate because, again, these cluster of measurements are not close to the true location at the center here. But they're precise because they're very close together upon repeated measurements. And then we have something here which is accurate and precise. So it's accurate but imprecise, in that all of the measurements are fairly close to the true value at the center, but upon repeated measurement, they're differing from each other, so they're not clustering. So that's not ideal, but that's certainly a better case than 1 and 2 over here. So 3 is a better condition to have for accuracy. And of course, our ultimate goal would be to have measurements that are both accurate and precise. Here we can see that these measurements are accurate. They're all very close to the true location at the center of that X and Y axes. And the values upon repeated measurement are not too different from each other. So when we talk about uncertainty, what we're talking about is how accurate something is and how, at the same time, are the measurements that we have precise. So accuracy and precision at the same time. But accuracy overrules precision in the case of uncertainty. So uncertainty just means what type of error do we have on some measurement that we might take in geographic space. Let's look at an example with raster encoding. When we use a raster model to represent reality, we are in fact admitting error into our location accuracy. So location accuracy suffers whenever we measure something or record or encode something into a raster representation of reality. So consider this cell at the center of this small raster. We'll just look at that cell. And there's the centroid of the cell. This is the cell's coordinate reference. So that if you ask for a coordinate for that cell, the coordinate, it will be reported as the center of the cell. In some systems, it could be the bottom left-hand corner or the top left-hand corner. But for now, we'll consider the location of a cell as given by a centroid. The coordinate for the centroid is are these values. So we have a easting and a northing, and these are in meters. So they're quite large values because of the coordinate system that's being used for this raster. Now, if we want to encode a point, let's say the point that is just right very near the bottom left corner, so this is a point that has the attribute or category of green. Once that point is within the cell, the entire cell then becomes green. And the coordinate for the cell becomes the centroid. This coordinate here, the original coordinate of this point, for which is now being represented by the raster cell, that coordinate you can see is different from that coordinate up there. So when we talk about truth here, in terms of true coordinates, with respect to raster, we're talking about the coordinate that we find on the original point representation. And of course, always remember that that point representation is zero-dimensional, but it also has uncertainty with respect to what it's measuring in the real world for location. So this is just uncertainty or accuracy, inaccuracy that's due to raster representation that we're talking about here. Now that any given point that is green and falls in that cell, like if it was up in this corner, still the cell represents that point, and that has very different coordinates again than the cell center. So now that that cell represents a point feature, the only coordinates we have are these ones up here. So no matter where within a cell the green point falls, a cell will represent the green point, and again, the true coordinates disappear, and all we have then, when we have the raster layer, are these coordinates here. So one thing you'll notice here is that for a cell to represent a point, the point must be within the cell, and it could be as far away as one of the corners of the cell and still be within the cell itself to be represented by that cell. So if we had looked at A, B, C, and D here, just in the corners of that cell, these would all have very different coordinates from the cell center. And a corner is as far away as you can get from the cell center and still be within the cell. In other words, the hypotenuse, if we just divide it like that, we then have a right angle triangle. And this hypotenuse is the longest distance within the cell. No other line, no matter where we draw the other lines, can be longer than the hypotenuse. And that's why we say that half the hypotenuse, right here, is how far a original point could be and still be represented by that cell, and then have that cell center coordinates assigned to it. So this leads directly to how we can know and calculate the location uncertainty due to simply representing something as a raster model of reality. So the positional uncertainty is what we're interested in. This applies to points, lines, and polygon boundaries that go through cells. Because a whole cell must be used to represent the location of any point, line, or polygon, or even an edge feature in raster, because all we have are cells to represent things. So if a point falls within a cell, then the cell will say point present, and the coordinate will be the centroid of the cell rather than the original coordinates of the point that fell within the cell. So looking at these two diagrams at the right-hand side, they look a little complicated to start with. But again, it's the same as we just saw on the previous slide. We have a single cell here, and it has a resolution in X and a resolution in Y. And then it has a hypotenuse right here. And for a given resolution, we can figure out what the hypotenuse is and divide it by 2 to get half the hypotenuse right here. And that tells us the location uncertainty of any feature encoded within that raster layer due to the cell size. And how we do that is using Pythagorean's basic theorem. So because a cell is square, we can have a right angle triangle. Even if it's not square, we can still make a right angle triangle. And then we say that x value here, x squared plus y squared equals z squared. So z, and we just have that little equation right there. So that's the length of the resolution in x, the length in y, squared, and then added together. That gives z squared, which is the hypotenuse, squared. So we have to take the square root of that. So to get rid of that squared, we simply take the square root of x squared plus y squared. And once we divide that by 2, we then have the location uncertainty due to raster, because that gives us half the hypotenuse. And that's fairly straightforward for any given cell. In particular, for 99% of the cases that we would use this for, we have square cells, which make it very easy to calculate. So we can if x equals y, so if the resolution in x equals the resolution in y, then z squared is simply 2x squared right here. And if we take half of the square root of z, just to get z again here, then we have the simple equation that z, which is half the hypotenuse, so that's that distance right here, is equal to the square root of 2 times the linear resolution squared over 2. So that's the equation then for positional error for any raster. All you have to know is the cell size, the resolution in x and y. And then you know how uncertain you are in terms of the position of something that you might report from the raster. So you may have a raster layer, and somebody in that raster layer may represent the location of grizzly bear dens. You don't have the original point data. All you have is a raster, and somebody asks you to report the coordinate. So at what coordinate should I put in my GPS to find this den? Well, the best you can do is give them the cell coordinate and tell them that that coordinate plus or minus the error is where you're going to find that grizzly bear den. So it's fundamentally important to understand that error. And again, this is just what Louis looked at in the previous slide on the right-hand side here, just illustrating the locations within a cell that a point could possibly be. So these aren't 1, 2, 3, 4, 5 separate points. They're just representing 5 possible locations. And again, showing that half the hypotenuse of that cell is the maximum distance a point could be within the cell, and having the cell then still represent the point. And that's how we derived our error here.